I'm Falko Kuester. I'm a professor in the Jacobs School of Engineering, co-PI of ALERTCalifornia and co-director. Of course, you've already met Neil Driscoll, our fearless leader. So we just reminded the other day, we're going to talk about AI. AI is easy, AV is hard. So, what are we doing at ALERTCalifornia? First and foremost, before we get started, everything we're doing is because we have an amazing team on the research, development, and operations side. And everything you're going to see today is really thanks to this team working continuously, really sweating over this every single day. And then it's a larger scale. It really takes a village to run a system such as ALERTCalifornia that really operates as a production network, but one informed really by fundamental research that can draw from the full breadth and depths of what we have in the academic environment to accelerate forward. So again, thanks to all the supporters, partners, contributors, and ultimately downstream data users, everybody that puts purpose into this effort being driven forward. Now, we live in California for a good reason. We all like the Golden State. In California, we do things at scale, big, right? It's the largest population of any of the states in the US, the third, which means there's a lot of talent, which is great. The third largest in land mass, that means there's a lot of area to innovate in. And then the fourth biggest economy on the planet, which means there should be resources to tap to drive all of that forward. Unfortunately, we also love our natural disasters, extreme events at scale, and there are many of them. And I think it makes sense to quickly look at what motivated really many of us to coalesce and create this convergence accelerator really here with in the UC system. Let's go back to 2017. And well, we had fires, and we had fires at scale. There were 9,270 wildfires burning 1.5 million acres. And that's a shocking number that's really hard to conceptualize. Let's say we're going to step outside the building, line up excavators or bulldozers for 2.5 miles inland, from the coast inland, and then drive all the way up to the Oregon state border, obliterate all of that. That's the area that burned in 1 year, right? And in an earlier talk, we heard that 1/8 of the state has burned over the last 20 years. It's just a stunning number and something that we hopefully can work towards mitigating better in the future. 10,000 buildings burned, right? Mind-boggling. Now we fast forward to 2025, last year, the LA fires, where we lost 16,000 buildings in a single fire, right? Just to put that into context, it's mind-boggling. The loss of infrastructure, the loss of life, the loss of communities, and then the ultimate financial cost going with all of it. What we have seen, though, is this rapid increase in regards to how these fires develop, how far and how big they get. The Thomas Fire in 2017 was the largest modern wildfire in California and the US at large, and came with tremendous implications. Unfortunately, these fires often don't come on just a single occurrence type interval. We have cascading events. In 2017, we had 17 atmospheric rivers coming into California that dumped 4 times the normal amount of rain. We had 6 to 12 feet of snow in the Sierra Nevada. And if you have burned hillsides and now you're super saturating that, that's really a recipe for disaster. At the same time, our water infrastructure, dams and so on, filled to capacity. In this case, the Oroville Dam reached a level where the spillways had to be activated. Unfortunately, there was a design flaw in that spillway, which almost took out the entire dam. It was sheer luck that somebody had observed that an alternative measure could be put in place to prevent it from collapsing. And as I mentioned, right, the atmospheric rivers saturating hillsides in 2017 in Big Sur. We had a massive debris flow taking out Highway 1, which was finally opened again just recently at scale. In 2018, January 9th, after the Thomas Fire in the Montecito area had obliterated vegetation at the hillsides, we had a massive debris flow where 15-foot worth of mud and boulders the size of houses, right, washed through a neighborhood, killing 23 people in the process. Just devastating events, but cascading events where one follows the other, right? Fire to atmospheric river triggering a debris flow at the end. If you look at the broader impact of these fires, right, on air, water, and soil quality, what we breathe, what we drink, what we ultimately eat, the impacts are just horrifying at times. And we need to come up with this better technology solutions, techniques to mitigate these as much as we can. So this is definitely not the view we want to see for Yosemite Valley or anywhere, right? Because it's a particulate matter that we're breathing this tremendous cardiovascular health implication. Now, if we jump to the East Coast, there was more that happened that year. We had a total of 10 hurricanes, right? Harvey, Irma, Maria, they're all sort of burned into our collective memory with 3,369 fatalities and, again, hundreds of billions of dollars in damage. So how do we deal with these types of events, and how do we come up with better techniques to document, to analyze what is happening out there? Just across the border in 2017, we had the 7.1 moment magnitude earthquake, again, tremendous loss of life, damage to infrastructure, and societal scale disruption. The next big one for California is guaranteed. It's going to happen. If we get lucky, it's not in our lifetime, but we shouldn't bet on luck. Let's be prepared and come up with the best possible mechanisms to mitigate risk. Right? So in a state that does everything at scales, including disasters, let's figure out how to best approach this. Let's talk a little bit more about fire. So I just saw on the projection here, QI 25, right? Almost around for 25 years. I was fortunate to join the Institute as one of its initial faculty right at the beginning. The 10 worst wildfires in history for California have happened since the Institute was founded, right? That should give all of us pause, right? And many of these at scales that are unfathomable. 20 years ago, a firefighter, we have many friends from Cal Fire here, would have said, if you had seen a 100,000 acre fire in your lifetime, this would have been plenty. You didn't have to do this again, right? Now this is a new normal. We are seeing these fires at that scale all the time, all the way to the point where we have million-acre type fires burning. And that's something, I think, collectively, we should say, we should not accept this. So if you look at the little timeline, we'll describe the Apple fire here, right? At 12:15, you have this very pristine environment looking right towards the horizon. 5 minutes later, you have a cumulus cloud forming above or behind the ridgeline that then becomes much more articulated 10 minutes later. 15 minutes after, it already looks very, very ominous as sort of foreshadowing things to come. And at 40 minutes later, right, this looks apocalyptic, something that we ideally do not want to see ever happening at scale. Now you throw in wind-blown wildfires, again, by the wildfire from 2017, where you have literally microclimate developing. We have 360-degree wind shifts, wind velocity changes, embers just ejected tremendous altitudes. So you literally have this fire tornado forming there, which makes it extremely hard to respond and adjust on the fly. So how do we get to a point where we can detect or at least confirm fires, where we can monitor fires and help our friends at Cal Fire, the fire departments, who run towards the fire, where most of us would say, okay, let's retreat carefully from those. So our approach is really to look at how do we use data, and not just any data, but better big data that can be turned into action for hazard resilience. And that comes in 3 phases. We need to know what the lay of the land is before an event. What type of fuels do we have? What type of biomass do we have? And with that, what type of biofuels, if we can assess the health of our biomass. During the event, can we early on confirm that the fire is burning, localize it, track it, and really provide actionable data to those that work on extinguishing and managing those events. Can we enhance situational awareness? And then ultimately, after the fire, can we assess what happened? Can we learn from it? The greatest travesty of any natural disaster or extreme event is not learning from it, right? This is as horrifying as these events are. This is also a living laboratory providing perishable data that needs to be analyzed, studied, and used to mitigate these events and effects in the future. So can we assess vegetation growth or regrowth after the event? How did the landscape change? Can we assess the air, soil, and water quality? And for this, we essentially said, well, we're here at UCSD, and many of our team are at the Qualcomm Institute. Can we really look at an integrative science and engineering approach for the extremes and connecting what we have on the engineering side with what our friends at SIO are doing, connecting our core strengths across a campus made a big difference. So the question is, how do we acquire the best possible data? How do we get the right sensor to the right location at the right time? How do we stream this data to where it needs to be? How do we curate it, document it, make it accessible? Ultimately, how do we analyze it, model it, simulate it, visualize it, engage with it? But how do we get into the data into the hand of the first responders, of the stakeholders, of the public at large to make informed decisions? And that really is all at the heart of what ALERTCalifornia is all about. So ALERTCalifornia is a state-scale sensor network that provides currently 1,229, maybe it steps by more, 1,230 sensors. It grows quickly, that provide continuous 360-degree coverage across the state and provide interactive control over that sensor network so you can reposition it as needed. But it's real-time data that's accessible to first responders. It's accessible to the public. So anyone, anywhere, at any time can go to cameras.alertcalifornia.org and look at any of these data feeds. And they're up and running 24/7, 365, which means we're acquiring 2.5 gigapixel or 2.5 billion data points at any instant in time. And by the time my talk is done, there are at least going to be another 100,000 frames plus that have been acquired, streamed, stored, processed, shared, analyzed, communicated. And that is always on as a system to help all of us. Where are these sensors? They might be on mountain tops, on towers, on masts. They might be field deployed, minimally invasive or not at all touching the landscape. They can operate in sensitive, environmental sensitive or cultural sensitive environment, or they might be entirely mobile, being deployed on the spot, connecting via satellite back into the larger network. What all of these sensors give us is a first-person view into the target environment, a continuous stream of the events unfolding as they're unfolding, but with combined information of where that sensor is placed, what it is looking at, what it is capable of seeing and contributing, before those data feeds come back in and get synthesized in our own command and control centers here on premise or at Cal Fire's north of south of ECC centers or the Cal OAS and similar equivalents. Right? So data feeds coming in at scale, providing us information about where the sensor network is, what its operational status is, but most of all, what the data feeds are, where you then can dial in, increase the level of situational awareness for a particular target environment or even for a particular event. Since all of that data is accessible in real time, you could do the nowcasting, assessing what's happening now. You can do the hindcasting, going back in time, using that information to inform what led up to a particular event, and potentially then the forecasting through forward simulation later on, predicting where fires go. Now, here's an example of one of the operation centers at Cal Fire, getting all of these feeds live to the respective decision makers so it can help inform the decisions, deployment scenarios, and so on that exist, but verify and validate what is really unfolding at a given time and potentially observe and confirm actions taken. Now, there's a lot of data out there, right? And in order to not be overwhelmed by it and get that watchstander fatigue, having these 1,200 feeds hammering you continuously, and you're not being able to see the forest because of all the trees, this figure of speech. There are different computational techniques that come in to provide support. And AI is one of those. It's not an exclusive one. It's not one that should always be trusted, but it's one that can provide meaningful information that, if grounded properly through subject matter experts, really help. So essentially, cameras acquire 360-degree information, continuously, look for anomalies. If an anomaly is detected, it's sent to the CalFire operations center. The operator there is really the subject matter experts, right? We are not firefighters. They are. They know what they're doing, but we can provide data. We're really good at acquiring, analyzing, streaming, providing access to data, but CalFire knows how to read that information, how to interpret it, how to act on it. And so the operations team essentially will look at that information and can classify it. Is this indeed the anomaly detected? Is this indeed a fire? Is it a wildfire, wildland urban interface fire, structural fire, vehicle fire, somebody burning off debris in their backyard? Is somebody torching a larger field? Is it a controlled burn? Right? So the CalFire operations teams can classify or characterize that data, and from there on, they marshal the response while we provide additional information going forward. And the data that now the operations team provides, the metadata on what is actually happening, is data we can pick up to retrain our system, which makes it extremely powerful. Right? And at times there might be just minute bits of information that a casual observer might have overlooked. The trotter fires starting after lightning strikes, right? They're very faint signals that the AI picked up, spaced roughly 15 minutes apart. But this ability to take over the network, zoom in, verify a signal being detected, right? The operations team was essentially able to check this out early on and then marshal a response. Behind the scenes, whenever an anomaly is detected, what really happens is that the system says, okay, for my particular sensor feed, I'm getting a signal. Let's figure out where that is by triangulating the position of that signal in image data using surrounding sensors. Since the network knows where other sensors are, we know what the view sheds are, so what's visible and what's occluded, right? You can actually pick the best possible sensor mix to contribute towards your answer. On the CalFire side, the operations team side, that means somebody can say, well, I'm going to be on duty during this particular time frame. I'm interested in this particular area of the state that I'm responsible for. If there are any anomalies, please send me a notification. And what the system essentially does for an event being detected, it grabs the respective frame plus a link into the sensor network, which is live. It maps the location, if possible, and provides essentially a real-time dashboard for that subject matter expert to work with. That gets pushed out either as an email, as a text message, as a call, based on what the user asked for. And then the end user, right, the subject matter expert at CalFire, can react on that and work with these data assets. The point being, right, data is being curated, shared ahead of time. That notification provides and gives full access to registered users into the network. So they can actually take over a part of the network and do whatever they need to do to get refined information. Right? The Tequila fire, for example, started with a little blip on the horizon, 60% likelihood that this was a fire. In this case, the user said, give me a call, sent me a push notification. That data went out. It was assessed, response marshaled, and then dealt with. And that has been quite successful. So as we said, the best fire that you could have is, well, is the one that never burns. The next best one is a fire that you detect, that you localize, that you respond to right before it ever becomes an issue. And the question is, how do you measure success? And there are different ways of doing this. We're still looking to fine-tune the best response. Historically, one has been, can the sensor network beat 911 calls, right? Does the system pick up information, signal before a human in the loop would see a fire, call it in, but with added benefits that you know where it is, when it started, how to get to additional information, how to confirm that it's actually there. Not somebody saying, Falko, you just called me up. Where are you? What are you looking at? Which direction? How far? Right? That's all time lost ultimately in marshalling response. So can we accelerate this quicker? And the ultimate measure is, can we change fire response in California? And thus far, the feedback from our friends at CalFire has been, yes, it does indeed make a big difference. So this gives us operational information about the environment we're working in. Data matters, but data matters beyond just the 2D feed. What we really want is a digital twin of the target environment, a higher dimensional model that allows us to literally put virtual boots on the ground, characterize what's happening in that operating theater. For that, we need to know what is the biomass and what is the carbon estimate for that environment. How would this burn when it keeps burning, right? If there's a particular trigger event shown. Can we, with that information, more reliably model wildfires? There's a lot of effort going on right now, and these are amazing directions that's being taken. And as engineer always cringe that many of these models are really underdefined. We just do not have enough data yet for the vegetation, the health of state of the vegetation that is present in combination with characteristics about the soil and soil moisture. But if we had this, that could be a game changer and will be a game changer in the future. As well as if you have remote sensing data, 3D, 4D data, can we do very quick change detection? And Neil alluded to this already. So over the last 2 years, ALERTCalifornia has been running a state-scale sensing effort for LiDAR image acquisition over 100,000 square miles of all high-risk fire regions to get exactly this data that we need to have available as a ground truth to do more digital twin synthesis, and then assessment, correlation, change detection in the future, and empower those that do large-scale simulation, right? And we said, if we have the data at scale, right, we have 18 plus points per square meter, LiDAR data, intensity data, multispectral data, we should be able to synthesize much more complex environments. And if you just very simply, cursory look at this, right, for Yosemite Valley, you see, well, there's green vegetation, there's gray or brownish vegetation, those are actually trees infected by a bark beetle. So vegetation that would be really resilient to fire, now that it's diseased through that bark beetle infestation, will become very powerful biofuel, right? So if you can understand these target environments, what they look like, suddenly we can take much more informed action. At the same time, right, regardless of where you are, if you can step into this target environment, that makes a big difference. If you now can synthesize hyperspectral information in real time, captured through aerial platforms, in this case from one of our drones, you get to see what normally cannot be seen, right? You make the invisible visible. So what is the hydration level? What's the presence of chlorophyll? What other particulate matter might be present in the target environment? So if you can synthesize all of this, this changes drastically. Now, if we can combine these two, the real-time situational awareness that the image-based sensor network creates with the 3D digital twin to give us better spatial awareness of where and when we are and what is transpiring, what information we can augment, right? So historically sense data versus lived sense data. So in this case, visualization of the different view sheds that the sensors take in, other data layers. If you can now synthesize these in real time, it completely changes how we analyze, how we understand these target environments. If you now can take that same digital twin, the trigger events for the fires or fire ignition points, take all the background data, boundary conditions, and we're able to plug this into fire models and do forward simulation, right? Of course, that would be a huge step forward as long as we can guarantee trust. That's still a lot of work that has to go into that arena itself. ALERTCalifornia's key objective right now is generate trusted data, inform future activities such as simulation, but to consider how that all would fit into our digital twin. A big part then is if you can ground truth everything in space and time, understand what happened in the past, what's happening right now, what could happen in the future, right? The question is, can we document change more readily? And through the remote sensing, either through aerial LiDAR scanning, through photogrammetry, we can now build very comprehensive 3D digital twins at scale, documenting change in target environments. If you can do this, we can actually ask our digital twin about what type of respective alterations happened and to vegetation maybe as part of controlled burn or other landscape preparation project. How did this relate to different processes unfolding later? Since it's all data, we should be able to in real time look at differences, right? Did something get removed? Did something get added? Did something get changed? So we can actually use the data to really tell a story rather than just being a powerful visual. So we're trying to converge between different sensor feeds and technologies. At times, we just need the real-world data. So I've been fortunate to work with Tara Hutchinson, who's a structural engineer, as part of our team on full-scale testing of both earthquake events and then cascading fire events, looking at how do we use robotic sensor platform in the context of at-scale structural system, and ultimately, right, how do we study this in the context of the wildland-urban interface? But having actionable data at scale, at a resolution where engineering decision-making is actually possible, right, is quite critical for us. So again, what's our goal? Use remote sensing to get 2D dynamic feedback of the world that surrounds us, synthesize it into 3D fully interactive digital twins so we can read, analyze, measure, right, collocate information. Combine that with simulation data that allows us to forward project and synthesize in situ information. So really giving the nowcasting, the hindcasting, and forecasting a voice to tell the story. But to tell the story in the context of these fully immersive virtual environments where we can study, analyze collaboratively, and really draw from each other's subject matter expertise. Okay, so what was this all about? Better big data for hazard resilience. What we really need is before, during, and after event information. What we need is the ability to build community efforts, right? And CalIT2, based on its founding agenda, right, really reimagined what an industry research park of the future would look like if it were in academia, moving from just fundamental research all the way to proof of principle to potentially production systems. We have demonstrated that this is possible, can have an impact, but really gel a larger community. Thank you so much.